Hello, today we're going to solve a classic calculus problem. Our goal is to find the total area enclosed between the curve y equals x squared minus 1, the x-axis, and the vertical lines x equals -2 and x equals 2. By the end of this video, you'll be able to visualize a problem involving areas, understand why you can't just compute a simple definite integral, and use absolute values to find the correct total area. First, let's understand why this problem is more complex than just calculating a standard definite integral. The definite integral from a to b of f of x with respect to x gives us the net area. This means it counts the area of regions above the x-axis as positive, and the area of regions below the x-axis as negative. When the problem asks for the total area enclosed, it means we want the sum of the absolute values of the areas. In other words, we want to treat all areas, whether they are above or below the x-axis, as positive. We don't want them to cancel each other out. To achieve this, we need to find the points where our curve crosses the x-axis. These points are crucial because they mark the boundaries where the function's sign, and therefore its position relative to the x-axis, might change. So our first step is to find these x-intercepts by setting our function, y equals x squared minus 1 equal to 0. Solving this simple equation gives us x equals 1 and x equals -1. These 2 points, -1 and +1, split our overall interval from -2 to 2 into 3 separate intervals. Now, let's visualize this. Drawing the graph of y equals x squared minus 1 is incredibly helpful. This is a simple parabola that opens upwards with its vertex at 0 and 1, and x-intercepts at 1 and 1, as we just calculated. The problem asks for the area between the lines x equals -2 and x equals 2. Let's draw these vertical boundaries on our graph. Now you can see why we need to be careful. The area from x equals -1 to x equals 1 is clearly below the x-axis, meaning a definite integral over this interval would give a negative result. However, the areas from -2 to -1 and from 1 to 2 are above the x-axis, and their definite integrals would be positive. The total area is the sum of the absolute values of these 3 separate areas. Let's calculate each of these 3 areas separately. We'll start with the first region, A1, which spans from x equals -2 to x equals -1. The area is given by the definite integral of our function from -2 to -1. The antiderivative of x squared minus 1 is 1/3 x cubed minus x. Now we evaluate this antiderivative at the upper and lower bounds and subtract the results. This simplifies to -1/3 plus 1, minus the quantity -8/3 plus 2, which gives us 2/3. So the area of the first region, A1, is 4/3. Next, let's find the area of the second region, A2, which is from x equals -1 to x equals 1. We calculate the integral of our function over this interval. Using the same antiderivative, we evaluate it at 1 and 1. This gives us 1/3 minus 1 minus the quantity -1/3 plus 1, which simplifies to -2/3 minus another 2/3, resulting in -4/3. As expected, we got a negative value because the curve is below the x-axis in this interval. For the total area, we take the absolute value, which is +4/3. This step is critical. Finally, we'll calculate the area of the third region, A3, from x equals 1 to x equals 2. We set up the integral for this interval. We evaluate our antiderivative at the bounds 2 and 1. This gives us 8/3 minus 2, minus the quantity 1/3 minus 1. This simplifies to 2/3 minus -2/3, which equals 4/3. Notice that this area is positive, as it should be. So, the area of our third region, A3, is also 4/3. We're almost there. We have the absolute areas of our 3 regions. The total area is the sum of these 3 values. Now, we just need to plug in the areas we calculated and add them up. This gives us 4/3 plus 4/3 plus 4/3. Adding these together, we get 12/3, which simplifies to 4. So, the total area enclosed is exactly 4 square units. Let's recap. We started by recognizing the key difference between net area and total area. We accomplished our learning goals by finding the x-intercepts to split the area into separate positive components. We then calculated the definite integral for each section and summed their absolute values to find the final total area. There's a neat shortcut we can use to double-check our work or solve the problem faster. Notice that our function, f of x equals x squared minus 1, is symmetric about the y-axis. This means f of x is equal to f of negative x. The interval we are integrating over, from -2 to 2, is also symmetric around the origin. This even symmetry means that the area on the left side of the y-axis is identical to the area on the right side. Therefore, the total area can be found by calculating the area from x equals 0 to x equals 2, and then doubling it. This requires only 2 integrals instead of 3. It's always a good idea to look for shortcuts like this in your math problems. Thank you for watching.